Give me a couple of minutes. At a meeting চলছিল, meeting থেকে আমি চেম্বারে ফিরলাম, আমি সব সেট আপ করে Am I audible? শোনা যাচ্ছে?
Yes, sir.
Sometimes I wonder whether you are actually there or I'm just talking to a tile of profile pictures. Anyway, so let me start. If we start from the last lecture that we had, let me share the screen. So we started with some modeling of the basic system like liquid charge tank system, and then we followed two approaches. That is, one is integral balance method. Another was instantaneous balance method. And finally, we saw that although the equations seem very trivial, but there is a catch that this relationship invariably involves a nonlinear function, right? Like for a flow-through valve, you can write the flow rate is directly proportional to the root over of the pressure head. So based on that, how this question comes, how do you tackle this kind of nonlinearities? And this is not a unique case. In most of the cases, in practical cases, we find this nonlinear behavior. So first, what we have to do, we have to linearize this, because all the techniques that we have for analysis and design of control systems, they're mainly focused on linear time invariant systems because they are easy to apprehend, they are easy to design, easy to tune, or easy to analyze. And most of the mathematical tools that are available are based on the principle that the systems are linear time invariant. But since it is by principle and on nonlinear system, so our first objective will be to linearize the system. So for that, we have found out the method of linearizing the nonlinear model via Taylor series expansion. Now this linearization is only valid within a narrow neighborhood or very restricted neighborhood about an operating point. What is an operating point? It can be thought of as an equilibrium point where the system is actually operating a steady state condition. Now, once a disturbance occurs, and if the parameters of the system or the behavior of the system is only slightly disturbed so that it remains within a small neighborhood, then we can approximate the system within that neighborhood by a linear equation, just like this, as you can see over here. So this is a method of linearization where we are considering small neighborhood about each and every operating point. And obviously, the linearized model so obtained will be different for different operating points. See, here the slope is this much, but in this case, the slope is completely different. So at different points, you have different kind of linearization depending upon the operating points. So it is very important that you first determine your equilibrium point, and based on that, you linearize the model and then analyze. So this much compromise you have to make while linearizing such nonlinear models. So there was one sort of school that is there. Otherwise, there is another stream of control systems that involves mainly nonlinear systems or nonlinear phenomena, that is nonlinear control, which incorporates all the possible nonlinearities, types of nonlinearities, and tries to handle them from a nonlinear point of view itself. They do not rely on this very restrictive approach of linearization about an operating point. That is beyond the scope of this course, but this linearization is very important because you may think that, okay, we have learned everything on linear time invariant system, but the system that I am actually operating with or trying to deal with is a nonlinear one. Then how to deal with that? So for that, this linearization technique will give you some idea about the system's behavior or how the system can be analyzed. And there are different conditions that you have taken into consideration. And based on this linearization, you obtain the dynamic model of the surge tank. And finally, there was a concept of deviation variable. That is, given a system is operating at a particular operating point or equilibrium point, if there's a perturbation, then the system variable, say output variable, will change with respect to that equilibrium value. And that particular deviation from the equilibrium value is termed as a deviation variable. And based on this deviation variable, it is normally modeled as a deviation variable model. So this deviation variation model basically describes the dynamic behavior. Dynamic behavior is the transient behavior that given a perturbation, how the equilibrium will change from one point to another. You can find out the new equilibrium by applying the steady state analysis. No dynamics is required. But how it is changing from one equilibrium to another equilibrium, what are the variables, what are the changes that is happening to the variables is depicted via this deviation variable model, which is a dynamic model because it involves a differential equation. Now we considered a very simple problem over here and derived its dynamic model, which came out to be like R by RCS plus 1. And interestingly, that is analogous to a series RC circuit where the capacitor voltage or the charge stored in the capacitor is your output. And we found the analogy of this electrical system with the liquid tank system over here. Next, we consider two such tanks. There is a coupled tank problem where two such tanks are connected in a cascade. corporate tank problem. And we found out that although each and every tank has a similar kind of a characteristics, but they do not simply shake hands with one another. That is, the overall transfer function from q bar to q bar plus q to q bar plus q2. Q is the input, small q, and small q2 is the output in deviation form, obviously, where q bar, every bar represents the equilibrium condition. Because at steady equilibrium point, whatever inlet is coming will be flowing to tank 2 and will be flowing out of the tank 2, so that the height h1 remains constant and h2 also remains constant. This is the equilibrium point, depicted by this bar over the head. And now if there is a change by an amount small q in the input, so there will be change in height h1 in the first tank. Correspondingly, flow rate between tank 1 to tank 2 will be changed by q1. That will cause a change in height h2 in the tank 2, and that in turn will cause the flow rate of the tank 2, exit flow rate of the tank 2 to increase to q2. So, although it seems there's a chain reaction, but it is not a simple chain reaction. There is a coupling term. See, had it been simple chain reaction, this could have been the transfer function, but there's a coupling term because this tank is basically loading this tank. There's a loading effect. And we know for transfer function, as I've seen in the RC circuit, cascaded RC circuit, the transfer functions are only derived when, or only valid when the circuit is not loaded. That is, there's no power is drawn from the output of the circuit. Like in open loop condition, it is only valid if you connect any load or if you draw any power from the circuit or the component, it will not be valid. The transfer function model will not be valid. That is the same case happening here. So what we have to do, we have to resort to the basic principle. So these are the basic equations of flow for this, where Q1 is equal to H1 minus H2 by R1, the resistance of this valve, and Q2 equal to H2 by R2, and so on. And this flow rate Q minus Q1 is C1 dH1 dt for this tank 1. There's a dynamic equation for height, and the dynamic equation for height in tank 2, C2, capacities of the tank, dH2 dt, the rate of change of height in terms of deviation variable, is equal to Q1, the water coming into the tank, minus the water coming out of the tank. So now if you consider this 4 set of equations and transform them into Laplace domain, I get this sort of equations. And we have seen that by incorporating this set of relations and then connecting the corresponding variables. See, I want H1 here, so this H1 will come over here. So I need H2 over here. So what is H2? H2 is given by this relationship. Now the output is Q1, and that should be connected to this one. Now that requires our Q2, and this Q2 will be coming from this, which is again related to H2. And Q1 is again taken back and fed back to this, right? And input 2s and Q2s is output. I've just written all the relevant equations in the block diagram form, right? Now just joining these respective variables in the order, we'll find a block diagram like this. Again, discuss kora hoyechilo, thik ache? There are loops, there are internal loops, there are feedback loops, and there are loops that connects. See, this loop is connecting these two internal loops. There, this is one closed loop, this is one closed loop. But since this loop is present, you simply cannot complete this or consider this as a single closed loop because this is also there. So we have to acknowledge the presence of this takeaway point. And for this loop, you have to acknowledge the presence of this summing point. It's a subtracting point. So how to take care of that? How to take care of this sort of a representation? I guess you have understood this the block diagram because I just incorporated the basic equations in terms of block diagram and then put the right variables where and as is required. And so I've got this comprehensive block diagram. So in today's class, I'll start from here itself and try to reduce this block diagram to the final transfer function form. So for that, I'll just again recap these things. These are first set of equations. Now I am getting this form. Let me show you. These are the four set of equations which is responsible for these four relationships. See, this relationship in Laplace domain will be h1s minus h2s by r1 equal to q1, this one. Then this relationship, this one. Then this relationship, the dynamic equation for tank 1. Okay, how we can write down this one? The Q, capital means obviously in Laplace domain, minus Q1 is equal to C1s H1, or you can say H1 is equal to Q minus Q1 by C1s. So Q minus Q1 by C1s. Similarly, for this case, H2 will be Q1 minus Q2 by C2s. Q1s minus Q2 by C2s is equal to H2. Now, if I combine all these four equations and four block diagrams and connect the right variables with its relevant input and output terminals, I get a block diagram like this. And this is equally applicable for the same for, have you had as RC circuit? Okay, so that could be the same block diagram, right? The different variables will be different. H, it will be Q1, sorry, voltage 1, voltage 2, like that. So now the problem is I can identify two very simple feedback loops. One over here, another over here. But the catch is this loop basically is joining or is doing a liaison between these two loops. So, because of the presence of this take-in point or takeaway point and this subtracting or summing point, you cannot simply obtain or reduce this loop and this loop. So, to be able to formulate or to reduce these two loops individually, what we have to do, we have to recast it in a form like this. What I've done over here, see this branch right? So I have shifted this takeaway point to here. So whatever signal I was taking over here, say H2S, this signal was basically H2S. So at this point, what is the signal? H2S by R2. But in the feedback, I want H2S. So what I have to do? I have to multiply that with R2. Agreed? So that this feedback signal still remains H2S. But there's another catch. I'm just advancing this summing point before even this summing point. Right? So if you consider this, so this signal when it was coming through was just going directly to 1 by R1. Now it is coming in before C1s. So it will be a signal multiplied by C1s. So this signal will be effectively H2S by C1s. But this should be H2S only, this signal. So what I have to do? I have to cancel out this C1s by multiplying this signal with C1s. So that means here it will come as H2 C1s divided by C1s. So it will be same as this. So by making this slight adjustments, that I'm this like block diagram algebra. This is basically block diagram algebra. Now I can recast them in this form. Now what is the advantage of this form? See, this is an individual loop and this is an individual loop. Now I can reduce these two loops individually. I put this over here. So once this is done, this loop, what does it looks like? This look like basically this loop is equivalent to any feedback loop of the form. Simply unity feedback, so I did not bother about that. It is RC, so C by R, G by 1 plus C. So if we simplify that, I'll get this over here. And for this loop, if we simplify that, I'll get this like this. So this is the cascade part that is normally expected. But due to this interaction between them, there will be this additional part. So now, in this case, your G has become right, and H as the feedback element has become R2C1S. So in this case, your total transfer function Q2 by Q will be G by 1 plus GH, which upon simplification will give you the desired transfer function. So this is another way of arriving at the transfer function just by mere block diagram reduction. And this is basically what we term as block diagram algebra or reduction. Reduction means to simplification. You simplify it and ultimately present it in a very comprehensive or this output by input a single transfer function like this one. So this will be this one. Okay. So see this problem, I think if you remember, I don't know whether I have the enough thing. Just let me show you, if you, just for your reference. I'll not be just recapping everything. So what I'll do, I'll just show you. I have that in our classwork. When you solve for this RC circuit, the cascaded RC circuit, and you've seen that the transfer function that you obtained, yeah. This was the case where transfer function. This is cascaded RC circuit, if you remember. So we dealt with the fundamental equations we wrote, then we went for the Laplace transform and then eliminated the variables, finally get this transfer function. It was quite lengthy. And we also used the help of complex impedance method because it was in electrical network. So by complex impedance method, we also obtained the transfer function, which was a bit simpler as compared to the fundamental method or the method that involves writing down the basic fundamental equations, then taking Laplace transform and elimination of a couple of variables. So there is another technique was complex impedance method where we transform the circuit into its S-domain equivalent and then find out the corresponding transfer function via simple. This is also a block diagram reduction, but this is not a conventional block diagram reduction. These are all impedances. And now we have seen the same problem. It is basically the same problem which can be dealt or which can be solved using this simple block diagram algebra or block diagram reduction. So it's very simple that given a particular, it's very trivial that given a particular network that you have to analyze, you can take help of either the first method, obtain the differential equation from the first principle, take Laplace transform, and then you obtain the transfer function after elimination of relevant variables. The second approach, if it is an electrical network or it's a mechanical network or any other network, convert it to analogous electrical network and represent the capacitor, resistor, or inductor if it is there by their equivalent complex impedances, and then reduce the circuit via algebraic steps to arrive at the transfer function. And third method is that you obtain the equations in Laplace domain, say from the first principle, and then represent the Laplace domain equations in terms of block diagrams or the sub-block diagrams, and then you augment or collaborate all these block diagrams to arrive at the final block diagram, and then apply the rules of block diagram algebra to finally arrive at the solution. So I guess the algebra that I've already introduced here, it might look like a jump because this signal notations, I've given you a class on this way back, I guess. Not here, I guess. Somewhere other place. Okay, anyway, so I'll just recap some of the basic ideas of block diagram algebra. Let's see. Let's start with some very basic problems, right? So given this network or this block diagram, I want to find out the relation CS by RS via block diagram reduction. Now see, these two loops are like interlinked. Okay, so either you have to bring this before this or and get this after this or vice versa. So just to have the block diagrams in a standard feedback form, what we can do, we recast this problem in this form. What I have done is that I have put this line over here. So the signal that was going through this and if you take a signal from here, so obviously this signal, say if it is x, so this is gx, and initially this was x, so this was x, and this signal was h1 into x. So I have to make sure that whenever I'm adding this to the summer, this signal should be h1 into x. This is x. But it is already multiplied by g. So what I have to do, to take care of this g, I have to divide this block or represent this block as h1 by g. So at the end of the day, I'll get the desired signal at this point. The question is, why we are doing so much mathematics? Because I want to represent each and every loop in a standard form without any interlinking. Okay? And the rest remains same. If this is x, so this is gx, and this is gh2x as usual. So now if it's x, gx, and so there is no correction required here. It is same as before. So finally the transfer function or the reduced block diagram will look like this. For this block, it is g by 1 plus gh2 standard feedback form, and this is feed forward form, so it is 1 plus h1 by g. Now, since they are cascade already, so the final transfer function will be given by g plus h1 by 1 plus gh2. So what is to be noted here, that the relevant takeaway points and the summing points, if you shift them, then you have to take note of the signals that will get altered. But you have to make sure that this alteration should not hamper the signal flow. Because the takeaway point, if you shift the takeaway point, the signal that it is taking now will have a different value. So just to take care of this difference, you have to readjust the gain, corresponding gain of the transfer function, so that I get the correct representation. Let us take a bit more complex example, then it will be much easier. Simply assume. এরকম তো আমরা করলাম, just we did this kind of example. Okay. এটা এখন অবশ্য বলবো না, it's very difficult. Let us try this one. It's much easy, and I think all of you can. খুবই সোজা আছে জিনিসটা। This is kind of a feed forward loop. I am taking the value from here. So this R, this is R, this is R, and adding them over here. So kind of a feed forward, not feedback. I'm not feeding the output back, but rather I'm forwarding the input to advanced summing points. So if you reduce this, something like this. Since I'm taking the same value R over here to the different input, so I take this to this as this to this with R, and this to this as this to this, same on. Obviously, I can do that. So from that, very trivial, I can write from this block what is the value 1 plus g1, and this is g2, and this is finally sum is there. So 1 plus g2, g1. Just multiplying these things. So this is a very interesting thing. So I just shown you this example. I've just shown you the example just to give an idea that closed loop system doesn't always involve feeding the input output back to the input. It may also have this direct feed through or a feed forward configuration. This kind of a feed forward configuration. Oh, that's right. Another phenomena that I just wanted to discuss. Another application of this block diagram algebra is kind of this, where I have a reference signal, and this is a block diagram. This is GF, is a feed forward part, and this is your feedback part. And this signal has a very significance. This is the disturbance part. Okay. Now, in some situations, we have to find out CS by RS. That is a response function, how the system is responding to the reference input, or CS by DS. That is how the response is changing under the influence of a disturbance. Okay. In either case, I can consider the other input to be 0. Then, when both the inputs are present, I can obtain the final response by just summing them because they follow the principle of superposition. So this is another application of this block diagram algebra. So what I will do here, so you have to find out the transfer function CS by RS and CS by DS both. So if you look at the set of equations that I have for here, so this signal US, what is the value? GF into RS plus ES into GC. Next, this signal CS, that is the output signal, is related to disturbance as well as this signal. So this is G1U. So D plus G1U, this signal, into GP, the plant. So this is the basic fundamental equation that we have. Now, this actuating signal, ES, is basically RS minus HCS or HSCS, whatever, right? So these are the fundamental equations that we can write right away. Now, after suitable algebra, okay, I can arrive at the transfer functions like this. CS by RS will be like this. And CS by DS will be like this. Now, I leave this as a task for you to obtain these two transfer functions using block diagram algebra. Right. The hint, obviously I'll give you some hint. I think for RS, CS by RS is trivial. We already discussed that. Okay, so in that case, DS will be equal to 0. Now, well, considering this DS, CS by DS, for this case, how we can recast this? You can recast this as is your DS plus GP, yes, CS. This is a forward path. And the rest of the things is entirely in the feedback path. So what will be there? In the feedback path, there will be H. Now R is 0. So GF will not come into the picture. So this H will come over here, followed by GC, right? And followed by G1. And since there is a minus sign, so it will be minus. Okay, this will be something like this. And this disturbance signal is very important because we will see when we will be discussing about open loop and closed loop control systems, or the effect of the feedback on control system behavior, performance, and all. Then this disturbance, as I've already mentioned in my introductory class, plays a very important role. Okay, and the feedback is mainly necessary to mitigate the ill effects of the disturbances primarily. So with this, I'll conclude the discussion on the block diagram. Now we shall proceed to the next part, that is a very important part, that is your time domain analysis. And time domain analysis is mainly time response. Now, time response means whenever we're trying to study a given system or the behavior of a given system, the main thing that we were interested about is how the system behaves when excited by an input or given a perturbation. And invariably, in each and every aspect of life, not only in system theory, in every aspect of life, we use the time as an independent variable and evaluate the output, or in some situations, state variables or states with respect to time. That is why it is called a time response. So I think I have mentioned there's a fine difference between the two terms, output and response. Can anyone enlighten us? What is the difference between an output and a response? Anybody? চলো কিছু তো একটা বলো। দীপজিৎ
Yes, sir.
বলো, আউটপুট আর রেসপন্সের ডিফারেন্স কি মনে হয়? What could be the, বলো না, whatever the thing that comes in your mind. Anyone can join. কি মনে হয় আউটপুট আর রেসপন্স? Don't be very technical. তুমি নন টেকনিক্যালও ভাবতে পারো। Just look at outside our textbook. Textbook বাইরে গিয়ে ভাবো না। Anybody else who can weigh in? It's very important. There's this slight difference, a fine balance, a fine difference between this output and response, especially in terms of a technical study. Okay, so I guess there's no answer coming from your side. Can anyone will give a try? Just try something. একদম বোবা হয়ে থেকো না, কিছু একটা বলো। আউটপুট আর রেসপন্স, হ্যাঁ বলো দীপজি।
স্যার আউটপুট মানে যেটা আমরা কি পাচ্ছি একদম মানে বাইরে সিস্টেম থেকে যেটা পাচ্ছি, তো মানে ওই আউটপুটটা যেটা পাচ্ছি ওটা মানে কিছুক্ষণ টাইম লাগতে পারে মানে জাস্ট স্টেডি স্টেটে যাওয়ার জন্য, বাট রেসপন্স আর ইনস্ট্যান্টেনিয়াস হয়।
আচ্ছা, ওরা বললে এনিবডি এলস, এনি আইডিয়া, আদার মোর, এনি আদার আইডিয়া? ওকে, বেশি ট্রাভার্স করবো না। ঠিক আছে দীপজিৎ, ওয়েল ট্রাইড, বাট দ্য কনসেপ্ট ইজ জাস্ট অপোজিট। Okay, output means given in instant. At any instant, you are given some excitation or some perturbation, and at any time frame or a snapshot of time, what is the value? There is output. Okay, at time t equal to 2, the value is 5. At time t equal to 3, the value is 6. So we call the output at time t equal to 5 is 6. We never say response at time t equal to 2 is 5. We say output. Now, what is response? The response is over the period of time. Say, we already mentioned steady state. Given a perturbation, a system takes some amount of time to reach the steady state. And the transient, this portion is called the transient part. And we try to represent this transient part as a response, that how it is responding. Not the instantaneous value or its value at any particular time. The overall range of time. And you normally represent response as a function of time, whereas output is normally represented as a solution to that function, right? Like if the response is represented as, say, I'm more comfortable with yt is some function of u, say input, and obviously time. So y of t1 is equal to f ut1, there is a fixed value. There is output at t1. But this expression itself, mathematical expression, this is the response. This expression represents how the response will be with respect to time. There is a time response. বুঝতে পারলে? আমরা এখন মেজার করি, আউটপুটটা মেজার করি, তাই তো? আমরা রেসপন্সটা মেজার করি না। তো নরমালি মেজার করি ইনস্ট্যান্টেনিয়াস ভ্যালুটা। এবার তুমি যদি টানা ধরো 1 মিনিট কি 2 মিনিট টানা তুমি আউটপুটটা মেজার করে গেলে, নেতিওটা রেঞ্জ অফ ভ্যালু পেলে, সেটা ভ্যালুস, এবার সেটাকে যখন তুমি রিপ্রেজেন্ট করবে, দ্যাট ইজ ইওর রেসপন্স। গ্রাফে রিপ্রেজেন্ট করতে পারো, একটা অ্যারেতে রিপ্রেজেন্ট করতে পারো, কিংবা একটা ম্যাথমেটিক্যাল এক্সপ্রেশন দিয়ে রিপ্রেজেন্ট করতে পারো, দ্যাট ইজ ইওর রেসপন্স। ওভার দ্য পিরিয়ড অফ টাইম, দিস ইজ ইওর রেসপন্স। ঠিক আছে? Okay, thank you. So this time response is widely defined as to be having two part, transient response and steady state response. Now, the transient response is very much important, and this is one of the major aspect of our study of dynamic systems, because this is a feature of a dynamic system. That is a system that involves some energy storing element, or it can store energy or convert energy from and convert that energy into suitable form as and when necessary. And this kind of systems invariably depict, or they invariably show a transient response while switching from one equilibrium point, that is one steady state, to another equilibrium point, that is another steady state, right? So this transient response characteristics is very important to know, because based on this transient response, we'll try to identify, or we'll try to first qualitatively state the nature of the behavior, and then to quantitatively state the time domain response or the time response of a system. Okay, based on this time transient response, this is main factor. But that doesn't mean the steady state response is of no use. The steady state response is also equally, if not equally, more important than transient response. Why? Because given a perturbation, first of all, you have to reach a new equilibrium, and that is a feature of a stable system, right? If you design a system which never reaches an equilibrium, then that means your transient is never ending. That system is of no use. So then you have to analyze the system and design a controller or tune the parameters of the system so that to ensure that it reaches a new steady state. That's important. Now, this steady state value should also satisfy your requirement. There should be some requirement on your part or the part of the customer or the part of the industry that given this type of perturbation, our response should reach this value. The steady state response should reach this value. So that is a primary. Say you have 10, 15 designs that ensures that your design is such that given a perturbation, the steady state response reaches the desired value. The next question comes, which response or which design should I consider? That decision will be made based on the transient response, because it can move over to the new steady state in a variety of ways that we will discuss. So in a sense, both of them are equally important, and you cannot say that this is more important and that is less, right? It depends. In some situations, the steady state performance is more important than transient performance, where you require the steady state to be reached. There is no scope for error, where you can compromise on the transient response. In other situations, the transient response is so restricted, then you cannot put emphasis on steady state error. That is the steady state performance. That is, you cannot say, I want this steady state performance strictly, but that might violate the transient response requirements. There are some physical restrictions out there. So either way, you have to make a compromise between both of them. And that is the part of a control engineer. When a control engineer is given a task, he has this Herculean task of managing all the facets, all the aspects, all the restrictions, and find the problem statement. Finding the problem statement where the transient response and steady state performance are specified quantitatively is more than half the work done. But finding the problem statement is the most difficult part. Okay, and that requires rigorous mathematical work, analysis, theoretical work, and like that, and a lot of experience. Right? So our assumption to study this, to continue with this study of time response, the first assumption is we have LTI system, and we will consider SISO, that is single input, single output system, and it's a stable system that it reaches a new steady state value, right? Okay. Now I have a very small query. Suppose given an input, I don't know what input is given. The output of a system is something like this. So what do you call? The output suddenly changes from this value to this value. So this is the input, suppose. Okay, let's make it very simple. Now this is output. So from this value to this value, as soon as you give an input, it instantaneously changes. So it's a static system, right? Static stable system. Now, if the system changes from this same state change, but through this one, the dynamic system, and this transition may happen like this, like this, like these are a variety of ways it can reach the final steady state value. So these are all dynamic systems. But if the response is like this, then you call this unstable. Because it's not settling down to a particular steady state value. Right. So that is a very concept. So our concept is that the system is stable. Now, how do we judge a system is stable or not? We have the technique of studying the Vivo stability of the system. So we can study the Vivo stability or find out, given a bounded input, if the output is also bounded or not. Then we find the system to be Vivo stable. And more importantly, before I go into the transient response to the time response analysis, the stability is also can be easily confirmed based on the location of poles of a system. Right? Now, what is a pole of a system? Given GS, which is a function of the complex variable S, where it is real part and this is the imaginary part. So we can always write GS as have two components. Right? Now, for every value of S in the S plane, there will be one corresponding value of GS, and that for every value of S, there is a corresponding value of GS. That is called single valued function. There is a mapping between S plane to GS plane is a single value. Now, if for every value of GS, there is an unique point in S plane, or this mapping is also single value from GS to S, then we call S plane and GS plane to have one-to-one mapping. Right? Suppose, for example, GS is equal to 2S. So for each and every value of S, we get a value of GS. Similarly, for each and every value of GS, there is one mapping, and you can write S equal to GS by 2. It's a one-to-one correspondence. Now, what about this function? From S to GS, what about the mapping? For each and every value of S, GS will have some value, right? But there is a catch. For S equal to 0, and s equal to -1, inverse mapping is not true, because gs tends to infinity will imply either s equal to 0 or s equal to -1. So gs tends to infinity will be mapped onto 2 points in the S plane, s equal to 0 and s equal to -1. So we cannot say at these 2 points the single is the gs and s are not following the rules of one-to-one mapping. And these points are called the singularities or the poles of the system. Now, what does this mean? I guess you know the concept of analytic function. What's the analytic function? A function gs in the complex variable of the complex variable s is called an analytic function in a region of the S plane if the function and all its derivatives exist in a region, then it is called to be an analytic function in that region. So as for our example, this gs s, the s is analytic at every point in S plane except at s equal to 0 and s equal to -1. So these are the singularities of gs, that is in common term are called poles of gs. On the contrary, this function, this is analytic in the entire S plane, and there is no singularity of this function gs, right? So this poles, this is the definition of a pole or the basic concept behind the pole. Okay, and now if we define pole, how do we define? So pole, if gs is analytic and single valued in the neighborhood of, say, a point pi, then it is said to have a pole of order r at pi if limit s tends to pi, s minus pi to the power r, gs is finite non-zero. What does that mean? If this GS contains a factor, say some BS, AS into, so it has a pole, at least these poles are there. I should not confuse this like this, factor like this. So when you multiply this by s minus pi to the power r, this will get cancelled out. So when you put s equal to pi, then the limit will be and that should be a finite and non-zero value. Fortunately, you do not have to dig so deep into this theorem. Given a transfer function, we'll simply term the numerator as zeros and denominator as poles. But the basic concept came from this analysis technique of complex variables. This is basically complex variable analysis, right? Similarly, you can have an idea on zeros. Now, why this concept on poles and zeros is important? Because we know, if you do not know, some of you may be aware that this stability and response, or the nature of response, primarily depends on pole location and zero location can affect the response only. Okay. Obviously, pole locations also determine the nature of the response and the stability. More important, the stability. If the poles are on the left half of S plane, then the system is stable. If it is on the borderline, this geometric axis, it is marginally stable. And it is in the right half plane, that means it's an unstable system. I guess all of you know that if this is the S plane, sigma, g omega, this portion, this open left half plane, is stable. Open means just barring this one. Open RHP is unstable. And this geometric axis marginally stable. So based on this, you can get an idea about whether the system is stable, unstable, or marginally stable just by looking at the pole location. So the main concern here is once you obtain a model of the system, then you can, just by looking at the model, you can predict the nature of the behavior of the system. Okay, this is the transient behavior of the time response of the system. So the second question comes, since we have been talking about analyzing the time response, so any response will require an excitation or input. So what input should you give to get a response or to analyze the time response analysis? There's a big question. Now, unlike in communications or in some specific electrical networks where we only use sinusoidal signals, in physical conditions, a practical system may be subjected to a wide variety of inputs. In some of the cases, the input functions cannot be represented by any simple mathematical law, or you cannot predict the value of that input that the system may be subjected to. So under such circumstances, studying the time response for every possible scenario is not possible, clearly not possible. In communication, it is possible. In communication, you know, it's a sinusoidal signal with different frequency. You change the frequency over a wide range and see how the communication attenuation or amplification is shaping up. But for all other physical systems, it's very difficult to study all the conditions the system may be subjected to. Then what is the way out? The way out is that you identify some set of standard test signals. Now, what are the standard test signals? This includes a representation of the different excitation or perturbations a particular system is subjected to, and these are the most significant perturbations or type of perturbations that a system is supposed to be subjected to. Second point, since we are only dealing with LTI system which follows the principle of superposition, if you can identify the systems or the test signals judiciously, then by a linear combination of these test signals, we can represent any random test signal or any random physical input by a linear combination of these test signals. Right? There's a two motivation behind that. That this should be the most significant, they should affect the system more severely or significantly. They should be more commonplace, they occur more frequently, and we should be able to represent any arbitrary input by a linear combination of these test signals. So let us see what are the different types of excitations or input conditions that severely strain a physical system. A sudden shock, there may be a sudden shock. A sudden change. A constant velocity or rate of change. A constant acceleration, rate of change of velocity. Now, a sudden shock means so how you can represent this in terms of standard mathematical signal? Listen, this signal below. Impulse. Sudden change. এটা step. Constant velocity. Ramp. Constant acceleration. That's it. Then you can go for jar and all, but this 4 is sufficient. So let us see how they can be represented individually. First of all, I'll consider impulse at the end. Step signal. So RT is equal to AUT, where UT equal to 1 for all t greater than equal to 0 for all t less than 0. And we have from this, so RS is equal to A by S. And how do you represent them graphically? This is step signal. Now, next we have ramp signal. RT is equal to AT UT for all t greater than equal to 0, equal to 0 for all t less than 0. And this is not required because UT is already defined as this. So what will be RS? A by S square. And the nature of the response will be it will have a slope like this. And there are the creative cheats. Then finally, parabolic signal. It has a nature like this, and defined as 80 square by 2 what actually is happening. See, step response, it was A by S. For ramp, it is A by S square. For parabolic, it is A by S cube. And finally, last but not the least, impulse signal. So actually this is now, if we have an impulse of, say, unity, that is RT is delta t, the direct delta function, for all t not equal to 0. Okay, where this del t, delta function, is defined as ddt of ut, and Laplace transform of this del t is normally 1. S into us, S into 1 by s, it is 1. And normally for step response, it is given as, for unit impulse, 1 by a, or you can write this as, this impulse function as limit epsilon tends to 0 minus epsilon to epsilon let's consider it a narrow band. This is minus epsilon, this is plus epsilon, and if you consider this to be the 0 point, or obviously this is not true, it's already true for this kind of scenario. This area for epsilon tends to 0 should be equal to 1, then call it unit impulse. Now, given this, let us now I'll conclude this class with the time response of first order systems. It'll take us 5 minutes more. So we have GS as 1 by TS plus 1, where T is a time constant. Now this can equivalently be represented as RS, as we have seen in passive RC circuit. Okay. So what is the transfer function? CS by RS, 1 by TS by 1 plus 1 by TS, the TS is multiplied for, that's fine. Now let us consider each and every input one at a time. So first, unit step. So your response CS will be equal to GS into RS, that is 1 by TS plus 1 into 1 by S. Now, to partially represent this as so this is the partial fraction expansion, or T will be there, obviously. So that can be represented as T দিয়ে ভাগ করে দিই 1 by S plus 1 by T. So taking inverse Laplace transform, your CT will be equal to 1 minus e to the power minus T by T for all equal to 0. Okay. So let us study this thing. So initially, what is the value of CT at T equal to 0? Is equal to 0. And finally, CT at T tends to infinity, T equal to T tends to infinity 1. So this is the steady state value, and this is the initial value. Right. And the most interesting part is at T equal to capital T, what's the value of CT? It comes up to 0.632. That is, when the output reaches 63.2% of, when the output reaches 63.2% of its steady state value, that is 1, that time is called the time constant. How do you represent them? Given an input, unit step input you have considered. The output response is something like this, and the time it takes to reach is calculated. Okay, so this is the definition of the concept of time constant. Now, this time constant has a very interesting definition. That is, it can be also depicted in other form. Slope at t equal to 0. What is the slope? That is dc t dt at t equal to 0. If you calculate dct dt at t equal to 0, what will be the dct dt? 1 by t e to the power minus t by capital T with t equal to 0. So what it comes out to be equal to t equal to 0 বসালে এটা 0 হয়ে যাবে 1 by t. So dct dt at t equal to 0 equal to 1 by t. This is the maximum slope. And what about the slope at t tends to infinity? Zero. So that means slope will be maximum at this point. What will be the slope? 1 by t. So how long will it take to reach the steady state of 1? Exactly 1 t. So had it been possible to maintain this maximum slope throughout the path, it would have reached the steady state in exactly t seconds. That is why it is called a time constant. But since it is not possible, the slope is continuously reducing, and finally at t tends to infinity, it is becoming 0. We are getting an exponential curve given by this expression. Right. That is an important aspect of this time constant form. Now, another thing is that we should also consider is the error. Where RT is the is equal to e to the power minus. So how the error will change? So at t equal to 0, what is the error? And t tends to infinity. So the error curve will change like this. And this et equal to 0 means at steady state, the output is equal to the input. So we get
স্যার অ্যাকচুয়ালি তো আমরা স্টেডি স্টেটে পৌঁছাতে তো মানে অনেকটা টাইম লেগে যায়। তো আমরা কোন টাইমটাকে বলবো যে সিস্টেমটা স্টেডি স্টেটে রিচ করে গেছে, মানে কতটা ওয়েট করব আমরা?
হ্যাঁ, এখানে there are two notions. One notion says you wait for the response to reach and stay within plus minus 5% of the steady state, or in some more restrictive notion is that it should reach and stay within plus minus 2% of the steady state. Okay, either 5% or 2%.
Okay, sir. Understood.
And the thing is that sometimes it happens that it doesn't reach, you do not know whether it will reach the actual input value or not. There will be some steady state error. So for that, you cannot apply this 5% or 2% rule. So invariably, you have to wait for it to settle down to a value. And normally for usual patch systems, they're quite manageable. But the only problem is that with the chemical processes or biological processes. In some of the situations, it takes around hours, even days or weeks to reach the final value.
Yes.
যেমন তোমরা যখন খেয়াল করে দেখবে, যখন আমাদের কোভিডের সময় যখন ভ্যাকসিনেশন গুলোর ওরা পপুলেশন করে সেটাকে মারার জন্য ভ্যাকসিনেশন ট্রায়াল করছিল, দে আর এ লং ওয়েটিং পিরিয়ড, বিকজ ইনস্ট্যান্টেনিয়াসলি তো কাজ করতে শুরু করবে না। to reach the optimum, the final value of the antibody, they have to wait for long. So it depends on different types of systems. Electrical system time constant যেমন খুব কম হয়, or mechanical system time constant বেশি হয় because of the inertia. Electrical system ওই জন্য এখন থেকে ম্যাক্সিমাম গাড়িতে ইলেকট্রনিক করা হয়, ট্রান্সমিশন বা ইলেকট্রনিক ট্রাকশন সব করা হয়। মেকানিক্যাল
তাড়াতাড়ি চলে আসে,
এক্স্যাক্টলি তাড়াতাড়ি সেন্সর রিচ করে যাবে, বিকজ nowadays everything you have to complete the task very fast, right? That is the problem. So this is the parts of the steady state response, and this is all for unit step. Now I'll just quickly write down the same thing for ramp and parabolic. I'll not derive anything, it's up to you to derive. That's another task for you. ডেরিভেশনটা করে রাখবে, পরের দিন আমি যদি কোনো ডাউট থাকে আই উইল ক্লিয়ার দ্যাট আউট। Unit ramp input I should write. Unit ramp input means unit slope. So in this case you will find your CS to be 1 by TS plus 1 into 1 by S square, and the partial fraction will be in this form. এরাটা তোমরা করে নেবে। And from that you'll get CT as something like this. Right? So what are the error? এখানে তোমাকে এররটা একটু, you have to consider error. ET RT minus CT, T minus T plus, so this T and T cancels out, so your ET becomes so at T tends to infinity, what will be infinity? এই পার্টটা 0 হয়ে যাবে, মাইনাসের বহে আছে, এই পার্টটা 0 হয়ে যাবে, so it will be capital T. That means in this case there will be a steady state error. So how does the response look like? Now, how's the input? Input is something like this. So this is your RT, and your response will be this, but it will follow some transient exponential transient, and then the final steady state value. So there will be an offset of capital T. This blue one is CT. So we can say that in this scenario, the output follows the input, no doubt, but with a finite steady state given by the value of T, which is same as the time constant. So if you reduce the value of T, then this response will become faster, fast, as well as it will give a less amount of steady state offset compared to a ramp signal. And finally, একটাই বাকি আছে, unit impulse. In this case, your RT is equal to delta T, RS is equal to 1. So your CS is equal to 1 by TS plus 1. That implies your CT will be equal to 1 by T e to the power minus T by tau. So is input like this. 0. And this is the value of 1. And output will be starting from T equal to 0. What is the value of CT?
Direct delta function.
Direct delta function. T equal to 0, what is the value? 1 by T. And T tends to infinity. C infinity is equal to 0. So starting from 1 by T, CT, and this red one is RT. ধরে নিচ্ছি অ্যাম্পলিটিউডটা 1 ধরে নিচ্ছি। ঠিক আছে? So this is how the response will vary. এখানে তো অফসেট এখনো ব্যাপার নেই, কারণ ইনপুটটা তো 0 হয়ে গেছে, তাই তো? আউটপুটটা আলটিমেটলি 0 হয়ে যাচ্ছে, নো অফসেট। এবারে তিনটে জিনিসের একটা প্রপার্টি বলে দিই, তাহলে পুরো সামারাইজ করে দিই। সামারি, unit step input, what was CT? It was, okay, not step first, so just first write ramp input. CT was T minus capital T. Now step. And finally, okay, I should write unit impulse. তাই তো? আচ্ছা, ইনপুট গুলোকে খেয়াল করো, এখানে কোনো অবজারভেশন কিছু বুঝতে পারছো? এনি কমেন্ট দ্যাট ইউ ওয়ান্ট টু মেক? কোনো অবজারভেশন কিছু আছে তিনটে ফাংশনের মধ্যে? একসাথে লিখলাম যেগুলো, কোনো রিলেশনশিপ বিটুইন দিস থ্রি ফাংশনস? Okay, look at the graphs. এগুলো দেখো। If you take ddt of ramp, what you'll get? The rate of change of rampটা দেখো, তাহলে কি পাবে? Step, because the rate is constant, তাই তো?
Yes, sir.
And what about
step কে করলে ডেরিভেটিভ
impulse? ddt of step will be impulse?
Yes, sir.
খেয়াল করো তো whether this is transferred to the output response CT, say C1t, d of C1t dt is C2t. আচ্ছা কি? তাই তো? Similarly,
yes, sir.
or reverse করো, এটাকে ইন্টিগ্রেট করো, C2 কে ইন্টিগ্রেট করো C1
মানে স্যার এভাবে আমরা ইনপুট দিয়ে একটা মানে ইউনিট স্টেটকে ইম্পালসে ট্রান্সফার করতে পারি জাস্ট
exactly you can start you can just observe একটা যদি তুমি রেসপন্স দাও that is why we will concentrate only on unit step response to study the transient behavior will only concentrate on unit step response কারণ দেখো if you know the step response function ct then you can easily convert it to ramp by taking a integration or impulse by taking a derivative. So you do not need to calculate all these ramp and impulse responses. Step function is a midway, is the right balance. Point number 1. Point number 2, step response is most easy to simulate in the laboratory. কিভাবে simulate করবে? এই ভোল্টেজ হিসেবে ভাবো সুইচ অন করবে কোনো ইনপুট নেই যে মুহূর্তে সুইচ অন করলে 1 ভোল্ট চলে এলো স্টেপ ইম্পালসটাও করা যাবে ইম্পালস যদি আমরা বাজার যেরকম করি প্রেস করে ধরে একটুখানি প্রেস করলে ইম্পালস দ্যাট ইজ অলসো ডান ramp at a physical problem is that there is a certain limit beyond which you cannot increase the input so it will be like this so ramp is not physically realizable but step is physically realizable and impulse as well but since step is midway between those two responses we will recommend unit step response to study the transient response if you understand or if you think that by studying the step response you will understand everything about a system then you will be wrong why see you can depict the transient response very accurately from the transient response analysis of step input for step input but what about steady state a given system the steady state is 0 for step same system but for ramp signal it's giving a steady state right so the steady state behavior of a system is input dependent so you cannot comment anything on the steady state performance of a system by just observing the or just by studying the step input response but as we already said we can comment on the transient response part for impulse or ramp just by studying the step input right since we're more concerned about the time response in the transient region only right now we shall only be concentrating on unit step input but that is not all to completely understand the time response you have to also comment on the steady state value and for that you need to find out the steady state behavior for each and every input like ramp and impulse okay I'll stop here so if you have any queries এই যে সব বুঝতে হবে জানেন কেন আমরা স্টেপটাকে দেখব ফার্স্ট ম্যাথমেটিক্যালি প্র্যাকটিক্যালি ওর সুবিধা হয় ট্রানজিয়েন্ট রেসপন্স অ্যানালিসিস করার জন্য ফর ট্রানজিয়েন্ট রেসপন্স ইজ এনাফ
বলছি একটু মানে আমরা সিপির ব্যাপারে আর কি আলোচনা করছিলাম
হ্যাঁ বলো
যে স্যার মানে আমরা মানে আমাদের ডিপার্টমেন্টে মানে বাকি ডিপার্টমেন্টের সাথে কারো আলোচনা হয়নি মেকানিক্যাল ডিপার্টমেন্টের সাথে তো স্যার 20 মার্চের পরে করলে আই থিঙ্ক মানে বেটার হয় তার আগে আমাদের
তো ডিপার্টমেন্টের শিডিউল চলে এসেছে ক্লাস টেস্ট উইকের তোমরা তো নিজেদের মধ্যে কথা বলো দেখো এক একটা ডিপার্টমেন্ট দেখে এরকম কথা বলবে তোমরা একটা কমন প্ল্যাটফর্মে আসো হ্যাঁ এসে কথা বলো বলে একটা ডেট ফিক্স করো তারপর দেখো 2-3টে অপশন দাও আমাকে আমি যেটা মনে হয় আমার জন্য কন্ডিউসিভ সেই ডেটেই তাহলে পরীক্ষাটা নেবো
ওকে স্যার আর বলছি মোডটা অনলাইনে হবে তো
এখন আমি শিওর নই গত 2 বছর অনলাইনে হয়েছে ঠিক আছে আমি একবার কনফার্ম করে নেবো আমার যে তোমাদের কোঅর্ডিনেটরের সাথে
ওকে স্যার তাহলে ওটা একটু আপনাদের বলবেন তাহলে আমরা সেই বুঝে আপনাকে ডেটটা তাহলে বলতে পারবো
তোমরা আমাদের তো অনলাইনের ডেটটাই বলো অফলাইন ডেটটা কথা আলোচনা করে রাখো ঠিক আছে
ওকে স্যার ঠিক আছে আসলে মানে এই সৃজন সংস্কৃতি আছে তো ওই জন্য
কবে থেকে সৃজন
স্যার 21 থেকে 24 আর সংস্কৃতি 29 থেকে আছে তো মানে তার আগে স্যার আমাদের মানে নিজের ডিপার্টমেন্টের সিটি গুলো আছে আর কি ব্যাপারটা
এটা মুশকিল হয়ে যায়, এটাই মুশকিল হয়ে যায়, মানে সমস্ত এখানে মাল্টিপল ডিপার্টমেন্ট থাকে না।
হ্যাঁ, আর কোন দিনে কি হচ্ছে তো সেটা সমস্যা। মোটামুটি 20-র মধ্যে যে নিজের ডিপার্টমেন্টের সাবজেক্ট গুলো আছে ওগুলো আশা করি সব ডিপার্টমেন্টেই মানে শেষ হয়ে যাবে।
আচ্ছা
সেই
আচ্ছা,
জন্যই ভাবছিলাম আর কি যে 20-র পরে হলে সবারই।
দেখো অসুবিধা নেই, যে অনলাইন মোডে হয় আমার তো সকাল বিকেল রাত কোনো সময় অসুবিধা নেই, কোয়েশ্চেন করে দেবো, তোমার সাবমিট করে দেবে। যদি অফলাইন হয় সেটা আমি দেখছি চান্সেস এর কম, লেস, বিকজ কোনো নোটিফিকেশন আসেনি, কোনো ডাইরেক্টিভ আসেনি,
ওকে,
সো আই ফলো দ্য লাস্ট ইয়ার্স ডাইরেক্টিভ, ধরে নিচ্ছি অনলাইনেই
ঠিক
হবে।
আছে।
ঠিক আছে,
তাহলে আমরা সব ডিপার্টমেন্টে একবার বসে আপনাকে তাহলে ডেটটা
একদম,
জানিয়ে
ঠিক
দেবো নেক্সট।
ঠিক ঠিক ঠিক।
ওকে, ঠিক আছে।
ওকে, থ্যাংক ইউ।
থ্যাংক ইউ।